Okay, perfect. Okay, welcome everybody to another MCRN colloquium. Just one quick announcement before we get started. So next week we will not have a colloquium. We'll instead have a welcome event for the mentoring pods. So we'll use this time that hopefully is optimal for people to do that. So if you signed up for the mentoring program, you should have gotten an email from the coordinators. If you haven't, let me know and we can connect you. But they'll put together maybe a 30-minute welcome event Monday, September 30th at this time, so that you can meet your pod members and coordinate the time for your pod to meet and all of those nice things. So just wanted to mention that so people are aware. I'll send that out in an email too. And then otherwise, today we'll be hearing from Emmanuel Fleurantin, who is a postdoctoral research fellow. He's associated with George Mason University and the Renaissance Computing Institute at UNC Chapel Hill. He's been working with Chris Jones, who we all know well from MCRN. And today he'll be talking about the Maslov index in dynamical systems and PDEs with recent applications and connection to stability. So with that, take it away. Thanks.
All right. Thank you so much, Christian, for this wonderful introduction. And it's great to give a talk at MCRN. So yes, like Christian mentioned, today I will be talking about the Maslov index in dynamical systems and PDEs, right, and some applications. And it's my hope that I make this talk as self-contained as possible. So I'll try to go as slowly and as general as possible, and then get into the details. I also want to thank the NSF for funding my position. All right, so let's get started. So in general, so why does stability matters in dynamical system, especially for climate? So this picture here, there's different like things that's going on in the world that I'm going to try to relate, right? So then first thing we could think about is tipping points, right? So Earth's climate system, it can shift suddenly from a stable to a chaotic behavior when critical thresholds or tipping points, right, are crossed. For example, a stable system helps prevent irreversible damage, right? So as you see on, so in this case, right, so basically you can see like there's floods on the right hand. So this would be like melting ice caps or rising sea levels, right, on both sides. And then another thing that could also matter is something called feedback loops. For example, here we have this describes a process in general that where the output of a system is fed back into the system as an input, right? So creating something like a cycle of cause and effect, right? So climate systems, they are interconnected, and stable feedback mechanism, an example that I could think about is carbon sequestration in forests, right? Regulate climate fluctuations, right? So a destabilized system can exacerbate problems like heat waves or drought, right? So that's why I had this sun here on the top. It's very hot on the right-hand side in this part there, right? And then the last thing that I could think about is long-term predictability, right? So then in general, like we like to do those things like we could use stability in dynamical system, and it allows for better prediction, right? And it helps like people, for example, that want to plan for agricultural cycles and also disaster preventions, and also helps with climate policy and safeguarding both ecosystems and human societies. Okay, so the outline of my talk will be as follows. So the first thing I'll do is I'll introduce the background, right? So I'll discuss the concept of stability in a dynamical system context, and I'll introduce the topological invariant known as a Maslov index. And also, I will also explain some connections between the Maslov index and stability. Now, the next thing that I'll talk about is I'll introduce some applications, particularly for the nonlinear Schrödinger equation, right? I'll discuss stability or something called solitary standing waves. I'll explain what this means in a minute, later on in the talk. I'll examine stability in a scalar case, and then, which is L plus, and this is an operator that I'll discuss about later. And then I'll also investigate stability using something called the GL operator, right? So, and I'll explain that when I get to that point, right? So then this is how I'm going to proceed. Okay, let's start with the background. So again, I'm trying to be as comprehensive as possible. So the first thing that we want to do is if we want to look at stability is understanding it, right? So I could think about if you have a dynamical system, ddtu is a f of u, where u sub t is in omega, which is the space that the solutions live in. This is the picture on the right-hand side. So now if I look at some examples, in an ODE, for example, omega could be a vector space, Rn, and the right-hand side could be polynomial. In a PDE, the omega could be a function space, in this case, L2R, and then the right-hand side could be partial. Now the spatial variable is introduced there as well. Okay, so then if I want to look at an equilibrium solution, i.e. a stationary solution, I'm going to set psi here, f of phi is going to be equal to 0, right? So this is what it means to be a stationary solution, right? And in the case where I'm going to look at temporal stability, so basically if you look at something is stable, is basically if a solution is stable, if I start near the solution, right, and then as time increases, I converge to it. And in the picture on the left, I mean on my right, in the solution is unstable is if I start near it and as time grows, I go away from, right? So then what is the importance of having stability, right? So I could think of like, you could, if you understand everything that's happening in the picture, you have all the equilibrium solutions, all the phase portraits, who's attracting, who's a saddle, etc. And you have intricate details about the invariant sets, stable and unstable manifolds, etc. And then you could assemble a comprehensive picture of the dynamics. However, if my system is highly nonlinear, this doesn't happen usually. Okay. So then the typical compromise, so what we do is like we usually find a stationary solution and then that offers some insight about how probable we are to encounter that solution. And then we could do some computations to get some understanding of what's happening near it, right? And even this can be hard because in particular cases, like if I'm looking at a PDE. Okay, now for PDE, stationary solution can depend on the spatial variable. So basically, if you look on the picture on the left here, you have a stable equilibrium point, right? So this basically, if I start in the point, I'm never moving, right? And the picture on the right here, this is a pulse, a stationary solution, where my right-hand side is f of psi, it's what you see here. So here, this psi of x is my equilibrium, a stationary solution, and the condition here is as x goes to positive and negative infinity, I decay to 0, right? So then stability analysis, right? So then how do we understand that further? So I could start with a stationary solution. So assume that I have a stationary solution here that meets the f of psi equal to 0. So then what I could do here is I could set up something called a stability ansatz, right? So basically I look at what happens to solutions that starts near the psi here. So then I could set up u sub t equals a psi plus v sub t, where my initial perturbation is very small. So then I could plug it into my evolution equation here and do a Taylor expansion centered at psi, and knowing that this f of psi is 0, so then I have this linear part plus this nonlinear part that follows, and I could set the df to be this operator L here, right? So then what I want to understand in a stability criteria is I say that the stationary solution psi is stable if solutions to this equation v sub t, if it decays to 0, right? This is some condition that I could pose. Okay, so then how do I assess stability? By looking at decay of perturbation. So there's different type of stability things that we could look at. We could look at something called an eigenvalue analysis, right? So we could look at the spectrum of this linear operator L here, right? So we say that it's stable, basically, if all the eigenvalues lie strictly in the left half plane, complex plane. And we usually call this spectral stability, right? So what about unstable eigenvalues, right? So then I'll talk about this when I introduce the Maslov index, right? So this could also be a little bit challenging. So then there's also this something called a semigroup decay, and this semigroup means like a family of operators, right? So this is L sub t, right? And then what I do is the semigroup when looking at this semigroup decay, right? So then I have this bound that I set up here, And usually this describes some linear stability, right? So, and then oftentimes spectral stability, right, commonly entails something called linear stability as a consequence of something called a spectral mapping theorem. So this solution to this linear system, V sub t is equal to L sub V, right? This is a general solution, V sub t, right? So now there's something else that we could also understand, which is the full equation dynamics, right? So then I could also look at solutions to the full nonlinear equation, how it decays, right? So this is nonlinear stability. And then oftentimes linear stability could imply nonlinear stability to a representation as you see below, where this e to the L sub t, right, is a matrix exponential representing the linear part of the system, and the integral term represent the cumulative effect of the nonlinear part in of u, for example. And this equation is known as a variation of constant formula or Duhamel formula, and then we will not focus on that. Okay, so let's get to the what we want to talk about, right? So what about the Maslov index, right? So where does it come into all this, right? So let's go ahead and try to understand everything, right? So the Maslov index, right? It extends something called the concept of a winding number, right? So what is a winding number? It's like measuring how many times a curve will wind around a point, right? So the Maslov index generalizes this idea to higher dimensions, right? And then and the thing that it's measuring is something that's something that's in the Lagrangian Grassmannian. And this Lagrangian Grassmannian is a manifold, right? It consists of all Lagrangian subspace of a symplectic vector space, right? And so then we'll proceed. So one by one, right? So how do we look into this? So we want to build the space, right? So we will begin by considering a symplectic form on R2N. And by symplectic form, this is something that's a non-degenerate, skew-symmetric, bilinear form on a vector space, right? So here it is defined as omega, right? So if I have PQ in my space, so this is how I define my symplectic form, where J is the structure that I apply to it. And J has this form. And usually if my system is Hamiltonian, I could easily extract this J matrix from it. All right, so next thing is I want to characterize the Lagrangian Grassmannian. So I got the symplectic form. Now I have the Lagrangian Grassmannian, and all it is this lambda n here. And what is this lambda n, right? So this lambda n it represents a space, basically where you have that all n-dimensional, it's a n-dimensional subspace of R2n, where where the symplectic form vanishes, right? So we want to make sure we add this restriction to that. So then basically, this is what we want to apply here for all PQ in this space. So then so we have the symplectic form, we have the space of Lagrangian Grassmannian. So now there's also something, if we want to look at the winding number, we want to look at paths, right? So we want to look at a path. So basically, we want to express path in lambda n. So then what we want to do here is we will look at frame matrices, right? This is what these A's of A and B are, right? Which is in Rn times n. So then this L here is going to be R2n times n. And usually these A's and B's, right? They're column vectors of the tangent space, right? So basically usually column vectors, and I'm tracking how these things wind, right? So I didn't say how I'm tracking it. All I said here is the setup to apply the Maslov index, right? So then these are the first things that I need to look at. Hopefully this is not too confusing, but I mean, I'll try to take my time to explain it, right? So another thing that we want to do is if I'm looking at path, the easiest way to looking at winding is to correlate it with an angle theta. And then I'll do something called a unitary matrix transformation. So what I want to do is I want to take this LT, right? And I want to apply this unitary matrix transformation. So a unitary matrix, usually it's a square matrix whose inverse is equal to its conjugate transpose. So it has some nice properties that I could use. here is I have L sub t. Remember, it has these frame matrices in there. And how I will get the winding is applying this formula. So e to the I theta t is the determinant, right, of of especially applied to this use of t. And how I'll do it, I'll take a minus ib over a plus ib, and I'll get information from that. In our particular example, we will call it det squared, right? So we'll take objects from this Lagrangian plane, and then it'll map objects from Lagrangian plane to the circle. So I'll get the winding number from that. And this is the formula that you'll see towards the end of my slides, right? So then, so what does that mean? So step by step again. So the Maslov index enumerates eigenvalues of use of t that cross -1 here. So then basically with multiplicity in direction. So basically now I'm looking at the winding of I'm looking at the number of eigenvalues of this unitary matrix that's cross a certain reference, -1 here. And I could do that. It's because it's related to the fact that the fundamental group of lambda n is the integer. So I could allow accounting, right? So basically, if L sub t is a loop, then the Maslov index is just the equivalent, its equivalence class, right? Basically, by looking at the winding of this plane, I'm able to do a count. Okay, so then what does the Maslov index also does? So it also allows me to construct to identify intersections with fixed reference plane, right? So D here is my fixed reference plane. It has this particular structure. So what this equation is saying at the very bottom right here, so this dimension of kernel of use of t plus I, of course, it measures the dimension of the kernel of use of t plus I, but it indicates where use of t intersects -I, right? And then on the right-hand side, so it tells me where L sub t intersects the reference plane here. So the equality in this case, it allows for detection of intersections with the reference plane and also allows me to count, right? So then the significance of this, it provides a computable, right? That's important. Criterion for detecting intersections, right? And it's important, right? Because it's important for calculating topological invariance like the Maslov index, right? There's a bunch of papers that talks about this. So for example, Arnold, 1967, Howard, Latushkin, Suktayev, 2017, and others, right? So that's the general overview of that for the Maslov index, or winding number. Okay, so then how do I bridge the Maslov index and stability analysis, right? So basically, the Maslov index serves as a tool, right? As you could see, it could help in some situation to enumerate unstable eigenvalues of linear operators, right? So then it's going to provide information if I'm looking at the unstable eigenvalues of instability, or in the absence thereof, stability, right? So this is the idea here. So then so we will start with a basic example, like something in lower dimensions, and we will move up from there to apply the Maslov index. And the example that I would use will have both flavors, right? So then where do we start? So we will consider, for example, in general, if we have this reaction diffusion equation where the diffusion coefficient 1 is 1 here, right? So then we have this parabolic PDE in one spatial dimension where U is a function in this function space here. So well, what we do is we have a stationary solution. We want to linearize about it, right? And we get this operator L here. So when we will focus on the spectral stability, so we will look for positive eigenvalues of L, right? Of this operator. So we said the eigenvalue problem, lambda v equals LV, subject to these boundary conditions. And the common technique is we will write a first order ordinary differential equation. Then we'll do a change of variables, and I'll show that specifically for my example. And then this change of variable will basically is going to put me from, for example, a rectangle to rectangular coordinates to polar coordinates. And then I could hopefully these two things decouple, the angle and the radius, and then I could focus on angular dynamics from there, right? That's the general idea. And then now So, well, how does this relate to the Maslov index? So in this case, I was fixing lambda and looking at the evolution to see if I get a jump, right? So now what I'll do here is I'll fix lambda and I'll vary the domain, right? So basically, what this will do is it will relate the Maslov index to examine how solution behave as the domain chain, right? So remember the Maslov index in this case will count how often certain subspace intersects. And for this particular case, it might count oscillations or turning points of solutions as the domain length varies, right? So you have something geometric, which is the Maslov index, and then we could look at it, we could compare it with something analytic like Sturm-Liouville, right? In this particular case. So then hopefully I didn't do too bad of a job, right, to explain what the Maslov index is. And hopefully this example that I'm going to present will do an even better job, right, at showing, the illustration of these two things that I talked about, right? So an application of Sturm-Liouville theory and then generalization using the Maslov index. And the equation that I'm going to look into is something called the nonlinear Schrödinger equation. So let's go ahead and get started. So then the nonlinear Schrödinger equation, I'm going to look at it in three spatial dimensions where I'm going to look at this particular operator, right, which is the mixed partials, right? So then I could think of this as an evolution equation on some function space, which is L2 sub R3 of complex valued functions, right? So in this particular case, right, so a lot of times you would see this represented as the Gross-Pitevsky equation, and you'll have in front of the Laplacian here a negative h squared over well, let me think, is negative h squared over 2m, right? So, and then you'll have plus, negative plus here. And usually h is like a reduced Planck's constant, m is a particle mass, and then v is, in this case, is going to be an internal potential, external potential. And then here, you in the middle, you have a psi square psi, so it's cubic, but sometimes there's a function g that represents the nonlinearity here. And usually you want this exponential, this at least is at least strictly greater than one. So g of, I mean, size of alpha, alpha strictly greater than one. But in this particular case, you have this plus here. It could also mean that this dispersion is inverted. So higher frequency component travels slower than lower frequencies. And having this negative here could mean that the regions of high potential corresponds to low energy for particles, right? And where does this stuff apply? So let's go ahead and talk about that. Like I said, well, okay, before I talk about that, sorry, I just got ahead of myself. So then we want to look at the setup conditions, right? So in this case, we're going to look at the radial case, and then we will look at the perturbed, the linear Schrodinger equation. So we'll add the perturbation epsilon. And then the only conditions that we want on the potential is that it may be any fixed potential, but we will take it to be exponentially decaying at both infinities. Okay. Well, I'm sorry, at positive infinity only. Okay, so then the applications, and I'll get into more detail about that. Relevance is like in physics, for example. I have like in the lowest energy single particle wave function, or the something called the Bose-Einstein condensates. This is where the Gross-Pitevsky equation applies. And then, well, basically, Gross-Pitevsky, it's used to describe the behavior of the collective wave function in the Bose-Einstein condensate, right? So in a Bose-Einstein condensate is a state of matter that occurs when a collection of bosons are cooled to temperature very close to absolute zero, right? So I'll explain more applications in a minute. In mathematics, right, we want to understand the effect of interacting nonlinearity and background linear potential in this case, right? Other applications that you could see, right? So in in real life, right? So we sometimes see it in ocean solitons and internal waves, right? So I got this picture from inkl.com. Okay, while it's not strictly modeled by a nonlinear Schrodinger equation, but we could use a nonlinear Schrodinger equation type. We could use an NLS type equation, right? So these nonlinear waves in the oceans, they are related and they can be visually striking. And they also play, as you can see here, a crucial role in ocean mixing and energy transfer, right? Which in turns affect climate processes, right? Another important thing that we want to look at is the idea of rogue waves, right? In the ocean. And I got this picture from this paper here. Is like there are unexpectedly large waves, right, that can pose significant risk to ships and offshore structures. And the NLSE type equations in this case can help predict the conditions under which these extreme waves might form. Lastly, we could look at soliton propagation, right? So we have a temporal evolution of a soliton here, right? And then in this particular paper, they use a stochastic NLS and they add some white noise, like in this case is random wind forcing, and they see how it behaves, right? So this could also help understand natural phenomena. Okay, so then what we care about, like you see here, soliton, so that's the keyword here. So then we want to look at solitary standing wave, right? So basically, when we say soliton, it's a stationary symmetric state. Okay, so then what we want to do is we want to first assume that a soliton U, right, which is real, exists and satisfy the corresponding stationary equation. So it needs to be a stationary solution. So it needs to satisfy this condition, set it equal to 0. So then U is a steady state solution. And fortunately for us, it is known that this such soliton exists for a very small epsilon in Dimitrios thesis here. And then the quantity mu here that you see on the tops of the screen here is a quantity that's going to indicate the phase of the wave. And well, the key point of all of this is we see that U is also time independent, which is great. All right, so then what we'll do is we'll make the following assumptions, right? So we have that the soliton is, of course, there's a scaling property, right? There's a scaling property on the nonlinearity here, right? In this case, it's cubic. And there's a scaling property that's associated for that's usually used for nonlinear elliptic equation, right? And for especially for our soliton, right, that allows us to set mu equals -1 in this case, right? So then there's papers by Sulem et al. Kasnav that indicates that. Remember that our soliton will set U, will assume U is real, right? It is. And then we also have that we're looking at the radio case, right? So use of R. Okay, so we have our soliton. The next thing that we want to do, like I've been presenting, is we want to linearize about it. So we'll look at the linearization at solitary wave. So then, but so we need to recast it, right? We have this I, so we need to recast it as a real system. So the first thing we'll do is we'll put the full equation in rotating frame. So we'll use this ansatz, size of I, um, um, phi sub I sub x, phi sub xt, right? So then basically, we know that there are solutions of this form, like there's a Marzola-Simpson paper that gives that. So once we recast it in a rotating frame, so we could rewrite the perturb NLS in real and imaginary parts. So we want to separate the real and imaginary parts. So we set the waves psi to be W plus IZ here. So then what we do here is we plug it back in, separate the real and imaginary part. And the last transformation here is we have that the soliton U is real. So we'll set W to be equal to U and then Z equal to 0, right? And then we'll separate the two equations. We'll separate two equations, right? So we'll have P sub T here and Q sub T. So, and then we have operators associated with them, right? And those operators, we conveniently name them L minus and L plus. So we could rewrite this P sub T, Q sub T as a first order system. It's a linear system, right? So then we have this L minus negative L plus, and this JL operator is Hamiltonian. So we could extract this structure that we certainly want to apply the Maslov index is the I negative I in the off diagonals. Okay, so we want to investigate this spectrum. So the eigenvalues that we want to look at, and I'll get into more detail in a minute, right? We want to look at, well, the eigenvalues, the spectrum, the essential spectrum will lie on the imaginary axis. So then the name of the game is to count the gap eigenvalues, right? So for this perturbed case, right? So I'm setting up the eigenvalue problem, but noticing here I'm using I lambda, right? So, uh, and then what I do here is I separate into L minus L plus, right? So then what I want to understand is I need to understand the spectrum of this GL operator. But of course, it's much easier to understand the spectrum of L or L plus and L minus in this case, right? So we'll take it step by step. And the reason why I use this notation here that you see at the top is so it's different things, right? So in the cubic NLS, right, the stability for epsilon equals 0 has been studied by Weinstein in 1985, but they look at orbital stability, right? So then, but in general, so orbital stability does not imply that the perturbation diminishes, right? The solution may uh, uh, continually oscillate about the soliton. What we want to understand is something called asymptotic stability, right? So that states that a perturbation of the soliton converge to possibly different but bound state in radiation, right? So this is important. So this is what we want to look at in this case. So then for this particular example, I hope like never clicked OK for the recording here. So hopefully it is going. So, but for this particular example, right? So because JL here is Hamiltonian, right? It has the spectrum has four-fold symmetry. So this is what it means, right? To have four-fold symmetry. And like I said before, the essential spectrum is made, it lies on the imaginary axis, and this is what it looks like, right? And what is essential spectrum here is the essential spectrum is just basically the continuous part of the spectrum, right? And there's also a point spectrum usually associated with that. And fortunately for us, our operator is self-adjoint, right? So then we don't have residual spectrum, right? So then what we don't want here is, right? So we don't want to look at the case where we have eigenvalues off the imaginary axis, right? So then we say that in the absence of any spectrum off the imaginary axis, the standing wave under consideration is stable. So that means that nearby initial conditions lead to solutions that do not meander away. So then what we want to show here is if there are no eigenvalues in the gap, then we can show stability in this sense. But, from simulations, we expect, I mean, from my simulations at least, we expect there to be eigenvalues when we turn on epsilon, right? And then the idea here is to count them, right? So this is what we do. So then the next thing that we do here is in the case where epsilon is equal to 0, in the case where we have no potential, right? This was already studied by Martin Simpson Marzola, and they have established that there are no gap eigenvalues, right? But so then we want to investigate the case where we turn on the epsilon, right? So what we do is to consider the spectrum of the Schrödinger equation with the potential. So then we have this setup here is the first thing is you want to go to from this Laplacian operator to this radial case. So we just kind of look at this Laplacian operator in 3D spherical coordinates. But because we assume radial symmetry, right? So then it only depends on R and not on theta or phi. Then the angular term vanishes and I'm left with the second line here in the green box. So then now I could rescale by dividing by epsilon squared here, right? So then this is my new equation that I get here where gamma is my eigenvalue parameter. All right, so then so I could define an index for the factual problem. So the count, so in this case, we'll say that the eigenvalue count that's generated by the potential, right, is going to be an eigenvalue of this particular operator, right? So in this case, I just set LP equals lambda gamma P and move everything on one side, but it's just seeing what was generated here. Okay, so then I'll try to be less technical, but the general idea that we want to do, we want to prove this theorem, right? So we want to say that let MV be the number of positive eigenvalue of Laplacian minus V on radial solutions. So basically, if I turn on epsilon, and if it's sufficiently small, then I could find gap eigenvalues in this interval, right? 0i, right? So in the case that I've been building here is like we want to show this or prove this by using a generalization of Sturm-Liouville theory based on the Maslov index. Right. But I'll start with a simpler case, right? So for L plus and L minus, right, the gap eigenvalues will be a negative 1, 0. And I'll show you how I use Sturm-Liouville oscillation theory to count, right? So, and I have this remark here, if epsilon is sufficiently small, then I could also do the same for L plus and L minus in negative 1, 0. Okay, so then that's a lot of information, right? So what I just presented already was, general notion of stability, and then tied into the Maslov index, present our example, or present the setting for our example, and what we want to do. So now I'll talk about, just how we're going to do that. And I'll start with the scalar case. So I'll look at the spectrum of L, right? So the first thing I'll do here is I have the eigenvalue problem, right? So I'll recast it as a real system by doing this transformation and looking at the associated equation for L plus is L minus. So then if I'm looking at the spectrum of L plus and similarly the spectrum of L minus, so this is my gap here between the star and the bracket. So epsilon is equal to 0. There's no gap eigenvalues. Epsilon is strictly greater than 0. Pop, eigenvalues start popping up, right? Depending on how deep my potential is, right? So I could set that by the way I define my potential, right? So then the name of the game is to count those radial eigenvalues, and I'll focus on L plus. So then how we do that? We set up the eigenvalue problem. So for L plus, L minus is essentially the same. So this is how it looks like. So we want to rewrite it as a first order system, right? So this is the P prime V prime here. And then so before I do this transformation, what is this P prime V prime? It's a linear system. And the good thing about this system being linear is this: if a line goes to the origin, right, it remains a line throughout its evolution. And then the characteristics that you have is induce a dynamical system on a one-dimensional real projective space, right? So, which is topologically a circle. So then I could do coordinate patches. I could take one patch to be P over V, and then another patch to be V over P, right? So then, but then this is hard to track. But to make my life simple, right? So what I'm going to do is I'm going to recast the system and just looking at the angle between this purple line here on my bottom left and a reference axis, in this case, the x-axis. So the easy thing is to look at theta arctan V over P, and then look at theta prime, differentiate both sides. So then I get this theta prime equation. So it decouples completely for R. And this R is not the same thing as the radius. This R is a domain variable, right? So then what I want to do is this theta prime is completely independent of, is decoupled, it's a completely decoupled system. So then the idea here is to understand what's happening from there. But unfortunately for this one, I have a 2 over R. So I have a singular term here. And my domain is also unbounded because my domain goes from 0, R goes from 0 to infinity. So I want to look at a compactified domain. So that's the idea. And then you'll see why in a minute. So looking at a compactified domain, so what I do is I extend the phase space, right? So then my phase space is now R2 cross 0 infinity. Remember, R grows, compactified by using this compactification parameter sigma. Apply this change of variable, so now I get rid of the singularity. So I'm looking at my compactified phase space in R2 cross 0, 1. So then as R goes to 0, sigma goes to 0. At R grows to infinity, sigma will go to 1. So then when I do this change of variables, right, so now I'm able to look at the dynamics at sigma equals 0, which is this P prime equals 0, V prime equals negative 2 over V here. And I'm also able to look at the dynamics at infinity, right, which is sigma equals 1. So I have P primes equal V, V prime equals this other part, lambda plus 1P, right? So then when at sigma equals 0, I have this line of fixed points. So I can look at the evolution of theta. Well, this line of fixed point for lambda strictly greater than negative 1, right? I get saddles. And then I could just kind of shoot from sigma equals 0 to sigma equals 1. That's the first thing. So now, remember, I want to simplify my life, right? So I want to look at the evolution of this. Well, this is going to be an unstable manifold by looking at unstable manifold coming from sigma equals 0 to sigma equals 1. And this unstable manifold is purely the angle. Nothing else to do here, right? But I want to look at the winding, right? So I want to go from R2 cross 0, 1 to S1 cross 0, 1. So when I do this transformation, so I'm looking at this unstable manifold winding around a cylinder almost. So then the name of the game here is the picture at the bottom. I'll start from sigma equal to 0. I'll shoot. There's going to be sets of fixed points. There's going to be center unstable, center stable. And then here is, since I'm going from in the gap -1 to 0, so it's the opposite direction. I mean, going down instead of going up. So basically here I go from 0 to the stable point here. You look at that total accumulation angle. Now at an eigenvalue, I will skip this and then jump down, right, to the next stable fixed point. Then if I jump by pi here, so whatever parameter that I fix to get this unstable manifold, this is my eigenvalue, right? So I separate the phase space into two different parts, right? So U epsilon means that in this particular part of the phase space, the soliton has a much more greater effect, right? And then this other part of the phase space, the potential has a greater effect, right? So this is the idea. So then what we do now is to look at angular variation of sigma, right? So this is how we count them, right? So then what we will do is not only do we want to count it, we could count it using the once we have that, we could easily do something on the computer to get the eigenvalue count, right? But we also want to prove it, right? So to prove it, we need to look at we're going to look at two different scales, right? So we're going to look at something called a sigma system, shooting from 0, but I need to shoot from infinity as well, which is the compactified space, which is which is sigma equals 1. So I need to have a similar dynamics that govern stuff coming from infinity. So that's the idea of what you see now. So then I set scaling, rho equals epsilon r, and because this is a potential driven system, I'll divide everything by epsilon squared, right? So then I get a new angle, a new angle, and then a new compactification parameter tau. And of course, there's a relation between tau and sigma. So as tau goes to 0, as tau goes to 0, sigma goes to 0. And as tau goes to 1, sigma equals to 1. So they match, but they're different scales. That's the important part. Okay, so then the eigenvalue the approach that I want to use for doing that is that I'll define spectral counting functions, right? So I'll call one x n sigma for the sigma system when I get jumps, and I'll call one for n gamma, right, for the tau system that indicates when I get a jump when something is the eigenvalue of my linear operator. Okay, so then the picture that you're going to see is the general idea, right? So I'm shooting from the left in the sigma system. These are the blue curves. I get a line of fixed points, so I could shift them up and down. And then I'm shooting from the right, right? Which is this tau system, which is this red here. I evolved both on a certain threshold that's equivalent, right? So then I assume that at the top curve, for example, I'm assuming that basically I have two two red curve that intersects this black line, and I assume that they're non-eigenvalues, right? So then I could use the intermediate value theorem, right, to show that there must exist a connection on this continuous distance in between them that connects one of these blue curves together and gives me a jump. That's the idea. Okay, but it's easier said than done, of course. Okay, so now let's look at the Maslov index. So everything comes together, right? So now we'll look at building up to the JL operator, right? So we'll set up the eigenvalue problem the same way, right? So we have L minus Q tilde is I lambda P tilde, L plus P tilde is minus I lambda Q tilde. This transformation, put it in recast it in a completely real system. Do this extra change of variable because it's going to give me a structure that I could exploit here, right? And we know what the L operator indicates, right? So then in the sigma system, so it's the equivalent, right, of the small sigma system, but this is the sigma system for the GL operator, is this 5D system, right? So I have PQ zeta eta, right? And then there's a comparable tau system for the behavior at infinity, right? So, okay, so then to put everything together, what I want to do is I want to look at eigenvalue lambda between -1 and 1, right? So then gap eigenvalues will occur, right? For example, when I have this JL minus lambda I, right? When it cannot be inverted, okay? So what I want to do here, this is how I set up the problem. So I have a sigma system. Now the tau system, I apply the similar scaling and have this gamma parameter for my eigenvalue. But what I want to do here is I want to introduce a new variable, right? And my new variable here is going to be this epsilon p here, the zeta equals epsilon p. And what it allows me to do is allow me to recast this tau system into a fast slow system, where the fast variable are this p zeta, and the slow variable are this um, um, q eta, right? So then what does that do for me, right? So it does this. So when u is equal to 0, this system decouples completely. So at infinity, right, when the soliton takes over, it has no effect. So my system is converted to something that decouples, right? So then the dynamics on the decouples are going to be the dynamics looking at the fast and slow system, right? Now for the slow system, the fast system, if I look at the phase space in R4, so by the way, the phase space is R4 cross 0, 1, of course. The phase space is R4, right? So the vector that span this R4, there will be a one associated with a fast system, one associated with a slow system. And then what we notice in our computation is the one associated with a fast system remains almost constant throughout the whole space. And then the winding coming from infinity is strictly caused by the slow system. So it is important to understand the dynamics of the slow system in order to get a good Maslov index count, for example. But this is just to prove it. But to count, right, using like computations, we will use the following approach, right? So what we tend to do is we want to track 2D subspaces in R4. So we will use local coordinate charts on lambda 2. So I'll recast, I'll use this coordinate patch here that I have. So I have PQ equals A zeta eta. So then then this allows me to look at the Lagrangian as the graph of A. Okay, so then I want to track 2D subspaces in R4, right? So this equation, I'm going to get a linear equation that's going to map 2D subspace into 2D planes, right? But I'm especially interested in Lagrangian planes, right? So then I look at what this A equation looks like, right? The evolution of it. I get a Riccati type equation, and this gamma inherits the symmetric structure that I want, right? So then what I do here is I compactify this system. So I have A prime sigma prime, right? So then I'm going to look at the sigma equals 0, right? So I'm going to look at A0 sigma 0, so typical ODE analysis. So this A sigma equals 0, A equals 0 correspond to the space eta zeta equals 0, zeta eta equal to 0, which I'll call X, right? So if I look at that, if I linearize it and look at the eigenvalues, it has 3D, it's 3D stable and 1D unstable. So now there is a 1D unstable manifold, which I call WU, that's associated with trajectories on lambda 2 cross 0, 1, which I denote by pi s sigma s. So now I'm going to talk about the formula that I talk about in the beginning of the slides, right? So there's this delta like function that I could take. So pi is a subset of lambda 2, right? But there's a formula that I'm going to talk about, the det squared, remember? That's going to take me from lambda 2 to S1, give me that winding. So if I want to do it computationally, so I go from lambda 2 to S1 by looking at the squared of a certain determinant. So if I view R4 as C2 in the obvious way, so this is the X and Y axis that you see on my left here. So this R is PQ and this P is zeta eta, right? So I look at this unitary transformation, right? So this pi, this line here is this U, which is real, of course. So we know that lambda sub 2 is isomorphic to the U2 over mod 0, 1. So what this is the space of Lagrangian plane is isomorphic to the quotient of unitary and orthogonal groups, right? So then what it means, like it makes me, I'm able now to show that, this is just showing that Lambda 2 is a 3 manifold, and the quotient is also 3 manifold, so the space equal to each other. So I'm able to use what I said in the beginning, look at pi, the vector that spans this unstable manifold, and looking at a unitary matrix transformation, just looking at this frame matrix, AB, where this is 4 by 2. And then I'm able to apply this det squared formula, right? So, which I said in the beginning, this is just e to the 2I pi. Something that's very great here, if I take the derivative with respect to r, the spatial variable here, I mean, in my case, so you notice that theta prime, right? It does not depend on theta, right? Only on delta, right? So then this suggests that the rate of change of the angle is determined by the Lagrangian plane itself, right? Not a specific representation. And then Arnold's formula, right? This is coming from Arnold's formula, right? It is used to get this theta prime, and this theta prime depends on all of this pi that's S dependent. That and then meaning is determined by the entire Lagrangian plane. Okay, so now I got it computationally. I could get the winding number from that. So I'm going to look at the angle accumulation that I get and see if it jumps by a certain amount, right? For whatever lambda that I fix and I vary the plane. So now how do I prove it, right? So then to prove it, the idea here is to obtain the full two-dimensional subspaces of decaying solutions, right? So now work in the Grassmannian bundle, G2 times 0. And what is a Grassmannian bundle? The Grassmannian bundle is a fiber bundle, right? Where each fiber is a Grassmannian manifold. So in this case, Grassmann bundles are important to study the global structure of my vector bundle. So I'll do the same thing, like in the case I did in the scalar case. So I'll set x plus to be in this space, right? But at coming from the pi equals 1 space, it's going to be the fixed point corresponding to the stable subspace of pi plus, stable subspace. And then pi plus will be its associated trajectory, right? So trajectory associated with the center manifold in the gamma system. So I'll have a similar thing, x minus, that's going to be a fixed point, or a fixed point per se. And it's going to have an unstable manifold, stable manifold trajectory. So the idea here is, and pi plus and pi minus, they are made of, well, candidate eigenfunctions of each corresponding to respective eigenvalues. So, right, what I want to do here is, and the set of the eigenvalue condition, right? So I'm going to be looking at the imaginary number I theta is an eigenvalue when the stable manifold, center stable manifold coming from infinity intersect the unstable manifold in, well, basically they intersect each other. So the intersection is non-empty, right? So then how do we show this? So computationally, right? This is the picture that you see on the left is det squared coming from the sigma system, right? So you see this angle here, and then what you see is that jumps corresponds to the lambdas for which I get an eigenvalue or potential that's deep enough. And then the picture that you see on the right here, this is that square calculation, but looking at the almost constant vector times the vector that winds, right, which is the slow system. So here, this is looking at the decoupled system and just doing this det square computation of those two vectors here, right, using this unitary transformation and using this Arnold formula, right? So you see it's a similar picture almost to the scalar problem. So then to prove this again, it's the same idea, right? So I x0 unstable fixed point, for example, in this G2 4 cross 0, 1, get an unstable manifold. So I have to say that, well, to show it, we looked at the decouples case, right? So remember from the beginning, we had a soliton driven system from the left and a potential driven system from the right. So this is what we have here. So the manifold, I mean, the fixed one x0 and the pi 0 trajectory corresponds to the pure soliton driven system. And then the one on the right corresponds to the pure potential driven system. We get them to get to a threshold. So now we want to apply the same thing that we did for the scalar case, some application of the intermediate value theorem, but we are in a different space completely. So what we want to look at an intersection of a train with a path, right? right? The train is going to be the train of pi 0, which remains steady in some that you see in the plateau region. And then I'm going to intersect it. So I have non-eigenvalues at gamma 1 and gamma 2, a path that connects them. And the amount of time this path intersects the train that's a cone here, that's the eigenvalue count. I'm counting the direction of and the amount of how many times it crosses, right? So then that's the general idea. And I hope I didn't confuse anyone, right? So I know that this could be abstract, but I hope you have some fun too. So that's all I got, right? So that's any questions on this confused guy that, like, what did I just talk about, right? So, and then these are some other references that I use. I want to thank you for taking about an hour to listen to me, and hopefully you enjoyed that. Thank you, Christian. I appreciate it.
Yeah, thank you, Emmanuel. That was great. Does anybody have any questions? We could take some time for that.
Emmanuel, thank you for a very exciting talk. I don't know much about the subject, but it was intriguing. So my question is, you use the nonlinear Schrödinger equation as your example. Are there any other instances where you might apply this theory?
Yes. So I've used it also in the case of a large deviation theory example. So for example, we looked at the escape, the most probable escape path. So you could imagine you have a stable point that's surrounded by a stable basin of attraction. So then we want to look at, under the effect of small noise, right? What is the likely path trajectory that this a path will take to escape this basin of attraction, or noise that's not vanishingly small, right? We have used the Maslov index to give us a set of trajectories that when you linearize about them, right, and you're looking at its spectrum, or you're looking at using some tools from the Maslov index, you could find that they're stable and they're associated with local minima of a certain action functional, right? And then using that, right, you're able to get a global minimum. So this is another application that use the Maslov index for.
Okay, thank you.
Quite well.
Sorry, I didn't
I said,
on camera.
I said you're quite welcome. Okay, sorry.
Okay. Any other questions?
Who was the guy in the picture?
It's a random guy. I don't know. The guy is completely random. He's a confused guy. That's very confused, right? So he's scratching his head and thinking about math, and he's confused about it. So, yeah.
Do his formulas make any sense?
They don't. They're just random. It's like when you're looking at
AI,
movies. Yeah, this is AI. Yeah. So when you're looking at movies and you see, like, somebody's thinking about math and you see all these random equations projected. Yeah,
Yep.
exactly. Yeah.
Okay. Any other last minute questions? Okay. If not, we'll post this to YouTube as usual. And if you come up with questions later, I'm sure Emmanuel would be happy to get an email or something. So then just one more reminder, next week we will not have a colloquium. We'll be doing a welcome event for the mentoring pods, but then we'll resume again the following week. I think Evo is next. I'll have to double check. So, okay. Yeah, great. Thank you all for coming, and see you next week if you're doing mentoring pods, or in 2 weeks if not.
Thank you.
Thank you.
Good seeing you.
Bye. And thanks,
Thank you.
Emmanuel. Great.
Yeah, thank you.